welcome to this problem walkthrough. Today, we'll explore problem number 323, number of connected components in an undirected graph. This is a fascinating challenge that tests your understanding of graph traversal techniques. We'll break it down step by step, analyze different approaches, and focus on the most efficient solution. Let's get started. In this problem, we are tasked with finding the number of connected components in an undirected graph. The graph is defined with n nodes, labeled from 0 to n1, and a list of edges. Each edge is represented as a pair, u, v, indicating an undirected connection between nodes u and v. A connected component is a subset of the graph where any two vertices are connected directly or indirectly, and which is not connected to any other part of the graph. The goal is to determine how many such connected components exist in the graph. For the input, we are given the number of nodes, n, and the list of edges. The output will be a single integer representing the count of connected components in the graph. Let's explore some examples to better understand the problem. In the first example, we have n equals 5 nodes labeled from 0 to 4, and the edges are 0, 1, 1, 2, 3, 4. Here, we can see that nodes 0, 1, and 2 are connected through the edges 0, 1, and 1, 2, forming one connected component. Nodes 3 and 4 are connected through the edge 3, 4, forming another connected component. Since no other nodes are connected, the graph consists of two connected components 0, 1, 2, and 3, 4. Thus, the output is 2. Now consider the second example, where n equals 5 and the edges are 0, 1, 1, 2, 2, 3, 3, 4. Here, all nodes are connected together through the edges, forming a single connected component that includes all nodes 0, 1, 2, 3, 4. Therefore, the output is 1 in this case. In the third example, we have n equals 4 nodes labeled from 0 to 3 and no edges, meaning edges equals. Since there are no connections between the nodes, each node forms its own connected component. This means there are 4 connected components, which are 0, 1, 2, and 3. As a result, the output is 4. These examples illustrate the variety of scenarios you might encounter, from graphs that are fully connected to graphs with no edges, and even graphs with multiple smaller components. Understanding these cases will help us design an efficient solution to the problem. There are some important constraints and edge cases to consider. The number of nodes, n, ranges from 1 to 2000, and the number of edges can be as large as 5000. Each edge is represented as a pair, u, v, where u and v are distinct nodes, meaning there are no self-loops. Additionally, there are no duplicate edges in the input. For edge cases, if there are no edges, such as n equals 3, edges equals, each node is its own component, resulting in an output of 3. In a fully connected graph, like n equals 4, edges equals 0, 1, 1, 2, 2, 3, 3, 0, all nodes are part of a single connected component, so the output is 1. Disconnected graphs with some isolated nodes, such as n equals 6, edges equals 0, 1, 2, 3, require counting both connected groups and isolated nodes individually. Here, the components are 0, 1, 2, 3, 4, and 5, giving an output of 4. Keeping these constraints and edge cases in mind is key to implementing a robust solution. To approach the problem of finding the number of connected components in an undirected graph, we first considered two main methods. The first is a brute force approach using DFS or BFS. Here, we treat the graph as a set of disconnected nodes and iteratively perform a traversal from each unvisited node. Every time we initiate a new traversal, it represents a new connected component, and we increment our count. While this method works, its inefficiency becomes apparent for dense graphs due to the overhead of repeatedly checking nodes to find unvisited ones. In contrast, the second approach we considered is union find, also known as disjoint set union. This method organizes nodes into disjoint sets based on their connections. Initially, every node is its own component, but as edges are processed, nodes are unified into the same set, reducing the total component count. With optimizations like path compression and union by rank, this method achieves nearly linear time complexity, making it highly efficient even for large and dense graphs. Another approach we examined is an optimized version of DFS or BFS. Instead of repeatedly starting traversals for each node, we maintain a global tracking system for visited nodes. Starting from any unvisited node, we perform a single traversal and mark all reachable nodes as part of the same connected component. The number of distinct traversals corresponds to the number of connected components. This method has a similar time complexity to union find, O, n plus e, where n is the number of nodes and e is the number of edges. However, it does come with limitations. For instance, recursive DFS can encounter stack overflow issues for very large graphs, making it less reliable in certain scenarios. Ultimately, we opted for union find as our chosen strategy. Its efficiency, simplicity, and scalability make it superior for this problem. Unlike DFS or BFS, union find avoids redundant node checks and handles both sparse and dense graphs with ease, all while circumventing potential recursion depth issues. The key to solving this problem efficiently lies in how we represent the graph and conceptualize the idea of connected components. Using an adjacency list allows for efficient edge traversal, and recognizing that connected components can be modeled as disjoint sets leads naturally to the union find approach. While DFS and BFS are intuitive, union find stands out due to its optimization techniques, such as path compression and union by rank, which significantly enhance runtime and memory efficiency. This makes it better suited for dense graphs and large datasets. In terms of complexity, union find achieves a time complexity of O, e asterisk alpha, n, with alpha, n, being the inverse Ackermann function, which grows extremely slowly. Space complexity is also efficient at O, n, used for storing the parent and rank arrays. These characteristics, efficiency, scalability, and straightforward implementation, make union find the ideal choice for this problem, providing a robust and optimal solution. To determine the number of connected components in an undirected graph, we start by understanding the input and setting up the necessary data structures. The graph is given as an adjacency list or matrix, where n represents the number of nodes and edges is the list of undirected edges connecting the nodes. One of the key data structures we use is a visited array of size n, initialized to false, which helps us keep track of the nodes we've already visited during traversal. Next, we build the graph representation. By converting the edge list into an adjacency list, we ensure efficient traversal. For each edge, u, v, we add v to the adjacency list of u and u to the adjacency list of v. This structure allows O1 lookup for neighbors during traversal. Once the graph is set up, we iterate through all nodes from 0 to n1. If a node hasn't been visited, it means we've discovered a new connected component, and we proceed to explore it. To explore a connected component, we perform a graph traversal using either depth-first search, DFS, or breadth-first search, BFS. Starting from an unvisited node, we traverse all nodes in the current component, marking each one as visited. This prevents us from revisiting the same nodes and ensures that the entire component is explored fully. For every unvisited node that initiates a traversal, we increment a counter that tracks the number of connected components. Finally, after iterating through all the nodes, this counter will represent the total number of connected components in the graph. At this point, we can return the count as the result, providing us with the solution to the problem. There are some important insights to keep in mind about this algorithm. First, by using DFS or BFS, we guarantee that every node in a connected component is visited before moving on to the next component. This ensures that our exploration is both complete and efficient. The visited array plays a critical role in optimizing the process. Once a node is marked as visited, it won't be revisited in subsequent iterations, saving unnecessary computation. Additionally, representing the graph as an adjacency list is both space and time efficient. This representation reduces the space complexity to O, v plus e, where v is the number of nodes and e is the number of edges. In terms of data structures, we use the adjacency list to store the graph, a Boolean visited array to track visited nodes, and either a stack or a queue depending on whether we choose DFS or BFS for traversal. There are a few edge cases to consider when solving this problem. In a disconnected graph with no edges, the number of connected components will equal the number of nodes, since each node is isolated. For a graph with just one node, there will always be exactly one connected component. On the other hand, a fully connected graph, where every node is reachable from every other node, will have only one connected component no matter how large the graph is. Finally, if the graph is empty, meaning it has no nodes at all, the number of connected components should naturally be 0. Analyzing the complexity of the algorithm, the time complexity is O, V plus E. This accounts for constructing the adjacency list and performing the graph traversal. The space complexity is also O, V plus E, which arises from storing the adjacency list in the visited array. Here, we are implementing a solution to count the number of connected components in an undirected graph. We start by building the graph using an adjacency list representation. This is done by initializing a dictionary where each node maps to an empty list, and then iterating through the edges to populate the connections for each node. Next, we create a set called visited to keep track of nodes we have already processed. Following this, we define a depth-first search, or DFS, function that takes a node as input. Using a stack, it explores all connected nodes, marking each one as visited and adding its unvisited neighbors to the stack to continue the traversal. This DFS function ensures that we can traverse an entire connected component starting from a single node. Now, we focus on counting the connected components. We initialize a variable components to 0. Then, for each node in the graph, we check if it has not been visited. If a node is unvisited, it means we have found a new connected component. We increment the components counter, add the node to the visited set, and call the DFS function to explore all nodes in this component. Finally, after iterating through all the nodes, we return the total count of connected components. This approach ensures that we efficiently identify and count all distinct groups of connected nodes in the graph. Here, we start by building the adjacency list representation of the graph. This is a fundamental step because the input provides the graph as a list of edges, but we need a structure that allows us to efficiently explore neighbors of each node. To achieve this, we use a hash map where each node maps to a list of its neighbors. First, we initialize the map with empty lists for all nodes. Then, for each edge in the input, we add the connected nodes to each other's lists, since this is an undirected graph. Next, we prepare to track visited nodes using a Boolean array, ensuring we don't revisit nodes during our traversal. Finally, we define a depth-first search, or DFS, function. This function uses a stack to manage traversal, starting with the input node. As we process nodes, we explore their neighbors, marking them as visited and adding them to the stack for further exploration. To count the number of connected components in the graph, we iterate through all the nodes. For each node that hasn't been visited, we mark it as visited, call the DFS function to explore all nodes in its connected component, and increment our component count. The DFS ensures that all nodes reachable from the starting node are visited, and by the time it finishes, we've completely processed one connected component. This process repeats for each unvisited node, effectively counting all distinct connected components in the graph. Finally, we return the total count of components. This approach ensures that we efficiently explore the graph while maintaining clarity and correctness in our implementation. Let's start with the first example where we have a graph with 5 nodes and edges connecting some of them. The goal is to determine the number of connected components in this graph. First, we build the adjacency list to represent the graph. We initialize an empty list for each node, resulting in 0, 1, 2, 3, 4. Then, we add edges one by one. Adding the edge 0, 1 connects nodes 0 and 1, so the adjacency list becomes 0, 1, 1, 0, 2, 3, 4. Similarly, adding the edge 1, 2 updates the list to 0, 1, 1, 0, 2, 2, 1, 3, 4, and finally, adding 3, 4 gives us 0, 1, 1, 0, 2, 2, 1, 3, 4, 4, 3. Now that the graph is represented, we prepare to traverse it. We initialize an empty set called visited to track visited nodes and set components to 0, which will count the number of connected components. Now we iterate through each node, starting with node 0. Since it hasn't been visited, we increment components to 1 and begin a depth-first search, DFS, from node 0. Initially, the stack contains just node 0. We pop node 0 from the stack, marking it as visited, and add its neighbor, node 1, to the stack. Then, we pop node 1, mark it as visited, and add its neighbor, node 2, to the stack. Finally, we pop node 2, which has no unvisited neighbors, so the DFS ends. At this point, the visited set is 0, 1, 2. Moving on, nodes 1 and 2 are already visited, so we skip them. For node 3, it hasn't been visited, so we increment components to 2 and start another DFS. The stack starts with node 3. We pop node 3, visit its neighbor node 4, and add it to the stack. Popping node 4, we find it has no unvisited neighbors, so the DFS ends. Now, all nodes are visited, resulting in visited equals 0, 1, 2, 3, 4. The final count of connected components for this graph is 2. Next, we look at a graph with 4 nodes where all nodes are part of a single connected component. The input edges are given as 0, 1, 1, 2, 2, 3. First, we build the adjacency list. Adding the edges results in the structure 0, 1, 1, 0, 2, 2, 1, 3, 3, 2. With the adjacency list ready, we initialize an empty visited set and set components to 0. Now we iterate through the nodes, beginning with node 0. Node 0 hasn't been visited, so we increment components to 1 and start a DFS. The stack contains just node 0 initially. We pop node 0, visit its neighbor node 1, and add it to the stack. Next, we pop node 1, visit its neighbor node 2, and push it onto the stack. Then, we pop node 2, visit its neighbor node 3, and add it to the stack. Finally, we pop node 3, which has no unvisited neighbors, so the DFS ends. At this point, the visited set is 0, 1, 2, 3. Nodes 1, 2, and 3 are already visited, so we skip over them. Since all nodes are part of one connected component, the final output is components equals 1. Now, let's consider a graph with no edges. In this example, we have 3 nodes but no edges to connect them. The adjacency list is straightforward 0, 1, 2. After building the adjacency list, we initialize the visited set as empty and set components to 0. We then iterate through each node. Starting with node 0, it hasn't been visited, so we increment components to 1 and begin a DFS. Since node 0 has no neighbors, the stack contains just node 0, and popping it ends the DFS immediately. Now, visited equals 0. Next, for node 1, it also hasn't been visited, so we increment components to 2 and perform another DFS. Again, since node 1 has no neighbors, the DFS ends right after popping node 1, and visited equals 0, 1. Finally, we look at node 2. Since it hasn't been visited, we increment components to 3 and start a DFS. Similar to the other nodes in this graph, node 2 has no neighbors, so the stack contains just node 2, and popping it ends the DFS. Now, all nodes are visited, and the visited set is 0, 1, 2. Since each node is isolated, the total number of connected components is 3. This concludes the walkthrough for this example, and it highlights how graphs without edges result in each node being its own connected component. The final output for this example is components equals 3. To analyze the time complexity of our solution, we can break it down step by step. First, we construct the adjacency list to represent the graph. This involves iterating through the edges, and for each edge, we add the corresponding nodes to their respective adjacency list entries. Since there are edges, this process takes time. Next, we perform a depth-first search, or DFS, to explore the graph. In the worst case, we visit every node and every edge exactly once. During the DFS traversal, for each node, we loop through all its neighbors, and collectively, this accounts for all the edges in the graph. Therefore, the total cost of DFS across all connected components is V plus E, where V is the number of nodes and E is the number of edges. Finally, there's the outer loop that iterates over all nodes to check if they've been visited. However, since each node is processed only once during DFS, this step doesn't add extra complexity beyond V. When we combine all these steps, the overall time complexity of the solution becomes V plus E, where V is the number of nodes and E is the number of edges. Now, let's examine the space complexity. The adjacency list, which is used to represent the graph, requires V plus E space. Each node contributes an entry in the dictionary, and each edge contributes 2 entries because the graph is undirected. Additionally, we use a visited set to track which nodes have been visited. Since there are V nodes, this set takes V space. Finally, the stack used during the DFS traversal can grow up to the depth of the graph. In the worst-case scenario, where the graph is one large connected component, the stack could hold all v nodes, requiring O-v space. These components together contribute to the overall space complexity. Combining the contributions from the adjacency list, the visited set, and the DFS stack, the overall space complexity of the solution is O-v plus E, where v is the number of nodes and E is the number of edges. Now let's compare this approach to a brute force method. A naive approach might involve repeatedly iterating through the entire graph to detect connected components. In dense graphs, this could lead to a time complexity of O-v squared, or worse. In contrast, our current approach leverages DFS to traverse the graph efficiently, achieving O-v plus E. In terms of specific scenarios, the best case occurs when the graph has no edges, meaning E equals 0. Here, the complexity reduces to O-v, since DFS is never triggered. For sparse graphs, where the number of edges grows linearly with the number of nodes, the complexity remains O-v plus E. In the worst case, for dense graphs where the number of edges approaches O-v squared, the complexity becomes O-v squared. To solidify why the time and space complexities are O-v plus E, we can look at the mathematical reasoning. During DFS, for each node, we process all its neighbors exactly once, which results in an overall cost of O-v plus E for traversing the entire graph. Similarly, the adjacency list, the visited set, and the stack used for DFS all contribute O-v plus E to the space complexity. These bounds are tight because every edge and node is visited exactly once in the traversal, ensuring no redundant work. Consequently, both the time and space complexities of this solution are O-v plus E, making it highly efficient, particularly for sparse graphs where the number of edges is significantly smaller than the square of the number of nodes. One common mistake when solving this problem is failing to properly mark nodes as visited. This can cause infinite loops in DFS or redundant processing in BFS, which can lead to incorrect results or inefficiencies. To avoid this, always mark a node as visited as soon as it is processed. Another pitfall is confusing directed and undirected graphs. Since this problem is specifically about undirected graphs, treating the graph as directed could lead to missed connections and an incorrect count of components. Additionally, using an inefficient adjacency representation, such as a 2D matrix for large graphs, can result in excessive memory usage. Instead, adjacency lists are typically the better choice for space efficiency. Lastly, starting DFS or BFS from nodes that have already been visited is a common error. This adds unnecessary computations and can throw off the component count. Always ensure searches begin only from unvisited nodes. Another mistake to watch for is neglecting edge cases. For instance, empty graphs, single-node graphs, or graphs without any edges can easily be overlooked, leading to runtime errors or incorrect outputs. Now, when approaching interviews, it's helpful to think of connected components as clusters of nodes, where every node in a cluster can be reached from any other within that same cluster. Articulating this intuition to your interviewer can demonstrate your clear understanding of the problem. Since this is fundamentally a traversal problem, make sure you're comfortable with both DFS and BFS. Be ready to explain their space and time complexities. Don't forget to address edge cases like disconnected subgraphs, self-loops, or graphs with no edges. Showcasing your awareness of these scenarios reflects thorough problem solving. If asked about alternative methods, you can mention the union find algorithm, which is particularly powerful for dynamic graph problems, such as when edges are added incrementally. This problem has many related problems that are worth exploring. For example, the number of provinces problem, also known as LeetCode 547, is similar but uses a matrix representation instead of an adjacency list. Another variation is friend circles on LeetCode 200, which also focuses on connected components. The graph valid tree problem, LeetCode 261, is about verifying if a graph is a single connected component and a tree. Additionally, redundant connection on LeetCode 684 deals with detecting cycles in a graph using union find. When exploring alternative approaches, DFS and BFS are the standard methods, and they perform well for both sparse and moderately dense graphs, with a time complexity of O-v plus E. Union find is another option, particularly useful for dynamic graphs, with a nearly O-v plus E *log** v complexity when using path compression. For smaller graphs, adjacency matrices can also be a straightforward choice, though they are less efficient for larger graphs due to higher memory usage. There are important trade-offs to consider between different approaches. For example, both DFS and BFS work well, but each has its own memory characteristics. DFS relies on the call stack, which uses O(h) memory, where h is the height of the recursion. BFS, on the other hand, uses a queue that can take up to O(v) memory in the worst case. Union find is another technique that offers excellent performance for dynamic connectivity problems, but it can be more complex to implement compared to DFS or BFS. Lastly, when choosing between adjacency lists and matrices, adjacency lists are far more space efficient for sparse graphs, as they only store edges that exist. However, adjacency matrices are easier to implement and may be a better choice for smaller graphs, even though they become less practical for large-scale problems due to their high memory requirements. Great work! Let's recap what we covered. We tackled the problem using DFS and Union find, reviewed their complexities, and highlighted when each approach is useful. Remember, graph problems are a core part of coding interviews, so keep practicing. Thanks for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!